All right, good afternoon, everyone. So let's get back to our discussion of convolutional layers. So this equation here summarizes everything. Here we have the input to the convolutional layer, which in this case would maybe be an activation from a previous layer, and the output, and this is the kernel. And the way that I like to think about it is if we focus on a fixed output channel M and a fixed input channel N, then the only thing left that's really happening here is we have a convolution of W over these spatial indices with this image here. So when we learned about those spatial convolutions, so we're essentially doing a separate spatial convolution from every input channel N to every output channel M. So we have a different kernel for every one of those. And then we're just summing across those input channels to get the mth output channel. Okay, so that's what's happening. And let's maybe look at it from another very tangible perspective. So here we have an input image that is color. So typically we write our color images, or we configure them with 3 channels, red, green, blue. And then these are describing essentially what we want to do. I think if I just describe it in terms of the goal, it should be clear, and then I'll describe it in terms of the convolutional filters. So our goal here is to convolve this image with this little red Gaussian blur filter. So what do you think should happen when I convolve this with this? What am I going to get at?
Another picture.
Another picture. Okay, is it going to be color or not? Or black or grayscale?
Grayscale.
Grayscale.
Peaks at when there's red.
When there's red, we should see brightness. When there's not red, we should see darkness. So, looking at this, there's a lot of red in this apple here, so we would expect to see some output image. It's a grayscale image that has light pixels in this region, but maybe dark pixels elsewhere. Okay, and then similarly, we're going to do the same thing for here, but now it's with a green filter, and so we would expect to get a grayscale image with brightness here and then darkness everywhere else. Okay, so that is indeed what we're going to get. So here you can see immediately there's three input channels, RGB, and there's 4 output channels, okay? And, but the way we can think about our kernel, if you want, is we can think about each one of these as really having this red filter is really, we can think about it maybe, there's like RGB grayscale filters that correspond to red, right? Because red, like in red, green, blue, red is just the first channel. There's different ways to do this. I'll show you exactly what we're going to do, but you could imagine doing this with, like if this is our RGB, and you looked in the red pane, you would see a grayscale image with brightness here. And then when you looked into this green channel of the filter, you would see maybe an all black image. And when you look at this one, maybe you'd see an all black image. And then maybe this pink one is a little bit more interesting because here, to make pink, you would need to use some combination of red, green, and blue that would be non-trivial, right? So that's another way we can view this, and that maybe makes a little bit more sense from how we described the convolutional channel before, because when we have 3 input channels and 4 output channels, we know that we should have 12 different kernels, 3 times 4. And here you can see the 12 kernels that we have. Okay. Is that kind of making sense? We're just viewing these 3 kernels together as a color kernel because we're humans and we can see in 3 colors. So it's just a shortcut. But I could have also shown you 3 individual pictures here, the ones for each channel. Okay. All right, so any other questions about about the goal.
So,
Yeah.
for example, in case of channel 0, what is exactly the kernel here?
I'll show you. I'll show you in the code. You'll see. So there's different ways you could make a red kernel, because red is a vague notion, right? One way to make a red kernel is you could make the first channel of this 3-channel thing to be a Gaussian blur, and you could set the other 2 channels to 0. That would be one way to make a red filter.
And will these 3 be the same?
So usually when you have equal red, green, and blue together, it makes white as a color. So in this sense, no, they would not be the same. Those 3 things would not be the same.
Actually, I'm trying to understand
Okay.
that we are saying that one kernel, for example, reddish, so it will give us brightness on reddish portion of the image, and otherwise it will be dark. And when it will be applied on that green one, green channel, so what is exactly that kernel that we are applying on these 3 channels?
So if we view the kernel in color, it looks like that color image. If you prefer to view it as a RGB triplet, each one is a grayscale, you might see the first one totally dark, R, the second one bright Gaussian kernel, green, and the third one blue, dark. Right, that's one way to make it.
And then that green of channel 0 will, how it will be different from that green of channel 1?
So okay, maybe I was confusing in how I wrote it here. Let me just. Sorry, let me erase this. Try to draw it differently. So you could say this, or you could view that as a triplet of the RGB components that make up red. So if I did it this way, you would see that in the top image, you would have the Gaussian kernel. Now, when I do this for the second green one, you would see, because again, we have red, green, blue, and I want to represent this, I would make that the green channel has a Gaussian blur filter, but maybe I would just leave these images dark, and that would give me this. Right? And then for the next one, the blue one, it would be the blue channel that has the Gaussian blur filter, so RGB, and then the other ones might be dark.
So there will be only 3 unique kernels.
Well, so this is, we're viewing it in color, but you could also think about it as a triplet of grayscale RGB. This is a triplet, this is a triplet, this is a triplet. So in total, there's 12 of these. So there's another pair. So these are, we can either say we have 4 color things or we have 12 grayscale things. Okay, all right. Okay, so yeah, so some of this we've talked about, but let me just give a few more details. So this color image is a tensor of shape 368 by 487 by 3. So this is 368, 487, and then we said there's 3 channels because it's color. And the way that we're representing it here, where you have vertical pixels, horizontal pixels, channels, this is how you write it in NumPy, and when you work with SK image, you work with this format. But that's not useful for PyTorch. For PyTorch, you have to transpose these coordinates. So we have to have 1, which tells us how many images in our batch. We just have a batch of size 1. We have to tell it how many channels this has, 3, and then we give it the 2 spatial dimensions. So you'll see in our code, we actually will need to do some data pre-processing to start with this, and then make it into that format so we can use it for PyTorch. Okay, so then the convolution layer weight matrix is a tensor of this shape. Number of output channels is 4. number of input channels is 3. K1 by K2 is just, you can almost count the number of pixels here. It's going to be 9 by 9. Each of these is a 9 by 9 kernel. And finally, this is the same equation that we saw on the previous slide that explains how the outputs are computed based on the input image and the this weight tensor. And yeah, there's a bias, but in this case, our bias is just going to be 0 because we're not going to add anything. Okay, so is it kind of making sense? All right, so let's take a look at some of the code. So the first thing we need to do, we're saying, okay, there's going to be one image in our batch, and this is the batch shape that we will want for PyTorch. So number of images, 1, number of channels in, 3 rows and columns. And then this is the command where we can change from the NumPy or SK image format to the PyTorch format. So this is the transpose command. So you're familiar with transposing matrices, right? If I have a matrix and I transpose it, that essentially means I'm swapping the indices, I for j, right? But when you have a tensor, transpose is a more general thing. It means like you might swap 2 indices, or you might swap all 3 in some way. So this transpose command basically tells you pick them in this order. First, choose dimension 2, then choose dimension 0, then choose dimension 1. So first choose dimension 2, then 0, then 1. That puts it in this order. Okay? So that's how we get that. But then we finally need to put in this, this extra dimension, and we do that just by saying, now reshape that according to this size. And so it's just going to say, okay, the data is the same. I'm just thinking of it as a 4-degree tensor rather than a 3-degree tensor. So that's what's happening here. And so now we have the format ready for PyTorch. All we have to do is do torch.tensor. Now Torch can recognize it as a torch tensor. And we're printing out the batch shape, and you can see this is what it is. Or sorry, no, I'm printing it in the demo, but I didn't copy and paste over here. But basically, this is the size that it prints out. Now this is where we get ready to make our convolutional layers. So we say number of channels in, 3, number of channels out, 4, kernel size 9 by 9. And then when we instantiate our convolutional layer from our neural network library, we have to tell it those things. And then it creates a model. And it initializes those model with random weights and biases. So now, as we saw before, we have to, well, what we can do is we can just take a look at the sizes that it made. So this is our weight tensor. And when you look at it, it's the shape is 4, 3, 9, 9, which is what we expect. Number of output channels, number of input channels, and then the kernel size. And then if we look at the bias vector, we just know that there's one scalar bias per output channel. There's 4 output channels, so that makes sense. Okay, everybody good so far? All right, so now we're going to make the desired weights because we have to replace the random ones that were initialized automatically by PyTorch. So the way we do this is actually kind of cool. We're going to exploit something that is very particular about these filters we created, which is that what happens in terms of brightness is completely independent than what happens in terms of color. In other words, let's say for this set of 3 filters, the brightness is highest in the center, and it decays in a Gaussian way as you go to the edges. But it turns out that all of the pixels have exactly the same color. They're all red with the same kind of red. Okay, and these are all green with the same kind of green. These are all blue with the same kind of blue, and so on. So what we can do first is just make a grayscale Gaussian blur filter, and then we'll use that. We'll combine that with the different colors later. All right, so let's, okay, I actually said it in the opposite order that we do it. So here's where we make our Gaussian kernel. We just tell it the kernel size, Gauss kernel, we call that function, and we have, how many rows, how many columns. This is the standard deviation. And so G is going to be our kernel. That's just brightness alone, and that's a matrix. Now, what about the colors? So for simplicity, when I was explaining this, I told you about one way to make colors, which is to make this kernel non-zero, according to this Gaussian shape, and then these other kernels exactly zero. But as you'll see, we're going to do things a little bit different, how we actually make the colors. So this is the RGB, so RGB. These are the RGB values that we used to make our red filter. Rather than using 1, 0, 0, we actually use 1, minus 1/2, minus 1/2. So you could say that this filter is definitely sensitive to red, but it's actually kind of anti-sensitive to green. When it sees green, it doesn't like it. It doesn't just ignore it. It actually gives like a negative output. Okay, this is just a choice for how we did it. We could have also done it other ways. These could have been different negative numbers or zeros, but this is just how it was done. And then when we look at the green channel, it's very similar. The green filter. So the green filter has a green channel at 1, the other channel's at minus 1/2. The blue filter, blue channel at 1, these at minus 1/2. And then this pink filter is half for the red and blue channels and minus 1 for the green. Okay, so these are just different ways to do filtering in the color domain. But notice that this is purely the color description. It has nothing to do with what's going on spatially. And then this is purely the spatial description. It has nothing to do with what's going on in the color domain. And so the way that we're going to combine it is we're going to use PyTorch broadcasting. This is a matrix that describes the color domain. This is a matrix that describes the brightness domain or the spatial domain. What we actually need is a 4-way tensor. We can make that 4-way tensor by using these two matrices. So what we do is we take the Gaussian spatial thing, we expand it to a 4-way tensor, and we just use none, none, which basically is, as we've seen before in other labs and demos, is sort of a way of saying to PyTorch, just like, repeat as needed. And the color weight, this is the matrix here, and then we're expanding this to a 4-way tensor with none, none, and then we're just doing a pointwise multiply. So this is going to essentially create this 4-way tensor that's going to have this going on in the color domain and this going on in the spatial domain. Okay, so it's an elegant little way of doing that. Okay, any questions on that? Okay, so now we finally have our weight tensor. We can just zero our bias, and we load these back into our state dictionary, load the state dictionary back into the model, and then doing a color filtering is nothing more than putting xtorch, our image, through our model to get ytorch, detaching ytorch back to NumPy so that we can plot it. And here are the 4 grayscale images we get out of each channel. And so you can see for this red filter, interestingly, it found most of the red in this orange here. For the green filter, it found most of the green in those 2 apples. For the blue filter, it actually found most of the blue in this apple. And for the pink filter, it found most of the energy in those 2. Let's see, is there, I don't know if there's more to say. I guess maybe what's sort of interesting is if you look at what happens in a black region of the image, you actually get like a gray output. So I don't know exactly what color map was used, but it could be that 0 in these images is gray, and that when you see black, that's actually like a negative number in the output, which is possible because we actually have negative numbers in our filters. So it could be that where you see black here is like where there's, according to this filter that has like this anti-green, anti-blue component, there's actually like that stuff is here, and that's why it's blacker than even the so-called background. Okay. All right, so yeah, and then this kind of stuff is what's happening inside a neural network. I'll show you other examples later. So, maybe this is your input, and then this happens in your first layer. Sorry, this is your first layer of your first convolutional layer, and then the features or feature maps that come out of it might look like this. And maybe these are somehow useful for classification if the color is really important to determining, what's an apple versus an orange versus something else. So this would maybe be useful information for the remainder of the neural network. Okay. Any questions? So just like a tangible example of convolution in PyTorch. So, I said that I would show you what was actually learned for these 11 by 11 kernels in AlexNet in the first layer. And this is what they are. So notice that if we think about the kernels as grayscale, there would be 3 times 96 of them. But we can also visualize the 3 kernels that take us from this color image to the first. We can view those 3 as a color kernel. And then there's going to be 3 more that take us to the second one, and so on. We could view those as a color kernel. And so that is what we see here. We have those 96 different color kernels. And this is what was learned to do classification in ImageNet. And so you find these shapes that are, it's interesting that a lot of the shapes are white, which means that they include red, green, blue components all together, that somehow the features they're creating are not really about color, they're just about shape. And what these are is essentially, if I would look across this direction, I would see things go up and then down and then up and then back to the middle. So it's some sort of little, you could say it's a form of an edge detector where the edge is in that direction. And then here is like a double edge detector when the edge is in that direction, and so on. Here is maybe like some kind of big, maybe this you could say is like looking for a thick edge, and so on. You could come up with your own interpretations of these. And we also have ones that are color sensitive. They're looking for when there's red in this direction and pink in this direction, and so on. Some of them are checkerboard type patterns. But for whatever reason, these are what it found most useful for that very first set of feature maps that would eventually become changed over and over again and finally be useful for classification. And these shapes are actually quite similar to what you find when you look at mammalian brains and you look at what kind of color patterns are exciting the neurons in our V1 layer. They actually look quite a bit like these shapes. So it's pretty interesting that that's what's learned by this neural network also. Okay, any questions on this stuff? All right. Okay, so now we're going to talk about a lot of different tricks that we need to do when training convolutional neural networks or deep networks. And so the first thing we'll talk about briefly is backpropagation. And as you'll see, there's a bunch of notation, a bunch more notation now than the last unit. So try not to get too distracted by all the details. Let's just focus on the high-level stuff. So what we have, in principle, looks a lot like what we saw back in Unit 8. So we have now many more layers, possibly many more layers. So we're going to use L to determine the number of layers. So you can see like these are the activations in layer L-2, L-1, and so on. And this ... means that there's many more of these here, but I'm just not drawing them all. So anyway, for any given Z, which we can think of them as the linear outputs of the outputs of a linear layer, you have the activations going into it, and then you also need to know the weights and biases for that layer, and together those things determine your scores Z. Those scores will go through an activation. Those activations will be used for the next layer, and so on and so on. And so when you think about the total number of parameters, we're going to have weights and biases for layers little l, 1 through big L. And if there's dense layers, they're actually, you can think of a dense layer as a special case of a convolutional layer with a 1-by-1 kernel. So that means that we don't really have to treat the dense layers any differently. We can just think about them as a special kind of convolutional layer, a simple kind. Okay, so this is what the forward pass looks like. So you initialize the first set of activations as your input X, and then you just do this procedure here for each layer little l. So this is just the convolution equation that we've seen a few times. Here's our weights. Now this is the weight matrix for layer L, the activations that are coming out of the previous layer, biases for layer L, and so on. This gives you the scores for layer L. And then those scores here are going to go through the hidden activation for layer L. But we also are going to have this kind of general thing which is going to represent the subsampling or pooling operation that might be in that layer. So maybe we're going to downsample by 2, or maybe we'll do max pooling or average pooling. And this is a sort of a very general thing here that I'm putting in all the indices because I'm saying what happens here could actually be different for every element within the batch. Like, because when you go through an average layer, it's actually using it's figuring out what it's doing based on the image. So you can still write it as a linear operation, but it's just that the value of that linear operation may actually be, determined by the exact ith batch element in the batch. And it may be specific to what happens is specific to the output indices K1 and K2, as well as the input indices J1 and J2, as well as the channel M. So everything's in there. It's just a way of writing the subsampling pooling operation that allows us to work with things tractably. Okay. So anyway, this is the forward pass. We go through this. We initialize all our variables, and then finally we have a loss that looks like this. So now this is the label for the ith batch element, and this is the final features that are output by the neural network for the ith batch element, and this capital L is for the Lth layer. And this is going to be a rank 3 tensor, which is made up from that last capital Z. Okay, so that's a forward pass. For the backward pass, the procedure is exactly like what we derived in Unit 8. We use the multivariate chain rule. Here, you just have to make sure that you're summing across, all the different variables that are appropriate. So, for example, when you do DJ dB for the bias for layer L and channel M, you have to sum over all the input channels, all the batch elements I, and all the pixels in the image or in the feature map in that layer. And basically, so this DJ DZL, this is something you can compute based on the cost. If you're doing regression, maybe it's quadratic. If you're doing classification, maybe it's cross entropy. We saw all the equations for this in the last unit. And then all this other stuff is very similar to the last unit, like DZL, DBL, and so on. You would get that from this, and it's very simple. It's just equals 1, and so on. So again, there's a lot of notation here, but I know you guys are capable of going through, and so I'm just going to focus on the high-level stuff. So one thing I want to point out is when you do this, when you compute this gradient, when you look at what remains, it has the form of a convolution or a correlation. So in other words, you have some, we can think about this as if it was a kernel, essentially. We can think about this as the input image to that convolutional layer, and then you can see that based on this structure here, it's really just nothing more than correlation, which is exactly what a convolutional layer does. So the point is, if you build or if you design like a GPU that's very fast at doing the forward pass, very fast at doing convolution, then it's also going to be equally fast at the backward pass. Very convenient, right? Forward, backward pass have the same structure. They're both based on convolutions. So we can continue and we can look at DJ, DA activation. And once again, you see exactly that same structure, except now we would technically call this convolution because there's minus signs, not pluses, but convolution and correlation are essentially the same. You just need to flip this around, flip it and reverse it, and then once again, you have correlation. So if you have a GPU or some architecture that's good at doing correlation, it's good for the backward pass as well as the forward pass, and so on. So this is just a pointwise multiply here. So basically, we see that at a high level, things are very similar to the backpropagation we learned before, and just that we have a few more variables to keep track of and convolutions to do instead of matrix multiplies. Okay. So that's all I wanted to say about backpropagation. Are there any questions? Anything here? Okay. All right, so we'll just talk about a number of sort of different topics that relate to training. So as we've seen, state-of-the-art convolutional neural networks involve millions of parameters. They require huge data sets for training, like ImageNet is gigantic, like in the millions. Also might require millions of iterations for training. So when you put all that together, you just have to have efficient hardware. Otherwise, you can't do this stuff. So conventional processors, CPUs, are not very good at this. They're not specialized to doing all these convolutions, over and over again at the speeds we need. So shortly after 2012, when there was these breakthroughs, then the people that work on the hardware realized, wow, there's an opportunity for us. They noticed that what was the kind of operations they were performing in GPUs at the time, just for displays, were actually very similar to the sort of things you need to do, in these kind of computations. And they said, well, we can probably just use a lot of that technology and just specialize it. And that's what they did, companies like NVIDIA. And now there's this massive industry of GPUs specifically for machine learning. And this makes a huge difference. So this is a plot from a few years ago, but what it's doing is it's comparing CPUs to GPUs. So let's just focus on this. This is when you have one GPU, and this is the time, so smaller is better. So I think this is the execution time. Let's see. Okay. Okay, let's focus on the blue curve. So the blue curve is showing the speed up against one CPU. So for this GPU, this was 30 times faster than a CPU. I think nowadays they're even faster than that. I mean, CPUs have also gotten a little bit faster, but probably not at the same rate. This is what happens when you have one GPU, but the GPUs can be designed that they work well together, and they actually scale quite well when you have just a few of them. So when you add a second one, the time reduces almost exactly by half, which is what you'd really hope. And now your speed up has actually gone from 30 to 70 times. So now you're 70 times faster than a CPU. When you go to 4, ideally it would be double this. It's not quite double, it's 130, but that's still really good. At some point, the returns are a little bit diminishing by the time you get to 6. It's a little bit faster, but it's not 50% faster and so on. But you can see you get quite a speed up, and to really train these big models, you really do need multiple GPUs. And companies like Google and so on, they have these whole data centers where they have just thousands of GPUs working on these models and being able to do things quickly. These things do cost some money, so if you want to buy a consumer GPU workstation, a nice one for machine learning, maybe you can do this for $3,000. If you want to buy a machine that has multiple good GPUs, maybe 30,000. If you don't want to invest that much money and you maybe just want to play with things, maybe you're a hobbyist and you like to take part in Kaggle competitions, you can rent GPUs for roughly $1 an hour. Now, there's many different kinds of GPUs. If you rent a really fast one, it's going to cost a lot more per dollar than if you rent a slow one or an old one. So this number, $1 an hour, is very rough. I would say this is probably for a very fast one. You could probably do cheaper if you use a worse GPU. But there's many companies that allow you to do this, Google Colab, many others. So if you click on this link, you get a list. So that's so for your final projects, I know that some students do like to take advantage of these resources because maybe they get frustrated that their laptops don't run fast enough. They'd like to train more models. Okay. Any questions on GPUs or anything like this? Okay. All right, so now let's talk about learning rate. So we learned about learning rate when we studied convex optimization. Turns out the situation there is very different. So when we studied convex optimization, we essentially saw that small learning rates are only bad in the sense that they make you get to the same solution, it just takes you a little bit longer. If you use a larger learning rate and you still can maintain convergence, it's nice because things speed up. Of course, if in that context, if you used too large of a learning rate, maybe your algorithm would have gone unstable and it's not good. But there's no real penalty for small learning rates except that it takes longer. It turns out that with neural networks or deep neural networks especially, small learning rates can actually cause convergence to bad local minima. So here's just an example, just a rough picture. So here you can see I have some local minima here. I have a global minima I want to get to. And so if I run gradient descent with small learning rates, what I'll do is I'll climb down and I'll stop here because now I've reached my minima, right? But that's not where I want to be. I want to be down here. So they had to develop all these tricks to try to get it to not converge there. So one trick is you actually take quite large step sizes. So maybe you take step sizes and then you hope that you can bounce out of that shallow local minima and eventually bounce into a good global minima. And because these global minima are often very deep, once you're in one, you tend to stay in one because it's hard to bounce out of it because it's so deep. So that's the idea. So actually, when you train deep neural networks, you want to use a large learning rate at first to escape bad local minima. And then, eventually, once you believe you're in a good global minima, then you can use a small learning rate. Because remember that if we're down here and we have this large learning rate, we'll just bounce around. We'll never settle at the bottom. So at that point, once you're in this domain of attraction, that's when you want to turn down your learning rate so you can get down to these low loss values. Okay, so this is called rate scheduling. Maybe I should call it scheduled learning rate. So the idea there is you determine in advance that you have this schedule, like I'm going to first go, I'm going to use this learning rate, and then I'm going to decrease it, and I'm going to decrease it, and then I'm going to decrease it. And there's many, many different forms of schedule. Like you could multiplicatively go down, you could exponentially go down, you could go down in steps, you can go up and down with a cosine. This one cycle strategy, this is the iterations and the learning rate. You can see that it starts at some value. It actually starts to increase the learning rate until some point at which it decreases the learning rate back to that level. And then at the end, it decreases the learning rate quite a bit, very close to zero, just to settle in that local minima. So there's many of these. You can read about them. We have all these green links here that describe them. It's a bit of an art, I would say. There's no single one that is the magic silver bullet for all situations. So try different things. Beyond this learning rate scheduling, another way to escape bad local minima is to use something like momentum. Momentum is something we saw, I think, in Lab 6. The idea is is when you're going in a certain direction, even when your gradient says you should stop because it's 0, you have some momentum that keeps pushing you in the same direction. And so the ADAM algorithm has momentum and adaptive step size and various other tricks inside it to try to escape these bad local minima. And ADAM is just one of many algorithms that are available to use in PyTorch. Okay, so that's what I wanted to say about learning rates. Trying to think. This is showing the value of the loss after a certain number of iterations versus learning rate. And so these are very small learning rates here. You can see that if you use those small learning rates, the loss you converge to is simply quite high. Once you start to get in this region, you can see you can converge to lower and lower. This seems to be kind of a sweet spot where you can get to lower losses. Now, if you go beyond that and you use learning rates that are very large, you have trouble, diverges. So there's sort of a sweet spot here. And there's particular ways to try to find what is this range. So this learning rate range test is one of the ways to do that. Okay.
This is like the final loss.
Yeah, this is the loss after a certain fixed number of iterations. So I think this actually comes from the paper that talked about that learning rate range test. It's sort of just a ballpark. So when you do this method, you need to figure out where to start. And then that's kind of how you can figure that out with that learning rate range test. Okay. All right. Any other questions about learning rates? Okay. Another very popular and effective technique is called batch normalization. So batch normalization, the intuition behind it is standardization. So when we studied regularized methods, we talked about wanting to standardize the raw features X, basically make them all roughly the same size, make them zero mean, unit variance, and that had various benefits. And essentially, that's one way to think about batch norm, is that for each channel and each layer, you want to standardize your features. And when you do that, that layer of that channel won't have to deal. There's different ways to think about it. Basically, it's like if it knows that the inputs are all within a certain range, it can use them much more effectively. If sometimes it has inputs that are several orders of magnitude above or below 1, it's just hard for that layer to know what to do. So when you initialize your neural network, you have to choose random numbers to put in all the weights, and you have to figure out like how big or small should those be. And the size you choose is proportional to the size of the inputs to those layers. And so this batch norm is one way to sort of adjust that. So here's how it works. So for each channel, so for the Lth channel and the Mth layer, Lth layer, Mth channel, this is just computing the sample mean, where you're averaging over all the pixels and averaging over all the elements in the batch. So with the sample mean, you can compute the sample standard deviation. You just take z minus its sample mean, then you square the results, and once again, you average it over the batch and the pixels. And here, just to make sure that this doesn't get too small, we're going to add a small number epsilon, so that even if this, like for some reason, goes to 0, that this won't go to 0, it will be lower bounded by epsilon. Once we have the sample mean and standard deviation, we can do standardization like this. So just subtract the mean, divide by the standard deviation. And here's, when you divide by this, you don't want to divide by 0, so that's why that epsilon's in there. Okay, so you could stop there, but the designers of this method said, well, maybe we should actually allow it to use a different variance or maybe standard deviation and mean that are learned. So we'll give it these learnable parameters, and we'll use backpropagation to learn those as well as everything else. And that way, if there are some better values than 0 and 1, it will learn them and it will benefit. So that's essentially how it works. So you compute the sample mean, sample standard deviation. That allows you to do this standardization here. And then you go beyond that by learning possible improvements to the mean and variance for that layer and that channel. Okay, is the idea making sense? Okay, so let me illustrate with an example. This is coming from the original paper. So here we have the number of training iterations, so going up to 30 million. And here we have the probability of error, or sorry, accuracy, the probability of correct classification. So, going up to like 70, 80%. And the baseline method, which is just this inception network, we'll learn about that, but it's the inception network without any batch norm. You can see it's getting up to this target accuracy, and it's a bit of an optical illusion. So let me emphasize that all these blue points are actually the same value. To me, it looks like these are higher than this, but they're actually all the same. Okay, so if we say that this accuracy, this green accuracy here, is the final one achieved by this method after 30 million some iterations, we'll say that's our baseline. Can we do better if we add batch norm? So the first thing we do is we add batch norm in red, and we can see that immediately just with batch norm, we can get to the same level in less than half the iterations. And in fact, it goes a little bit beyond that, a little bit better. But maybe that's not all. Maybe what we can do is actually increase the learning rate by a factor of 5. And what we see then, that is the dotted line. In that case, it's way faster convergence. And it's hard to tell if it gets better. But what if we increase the learning rate by a factor of 30? Now, you can see we're actually able to get way better performance than the original. So we actually have a pretty big increase in accuracy. So just an illustration of how well batch normalization works. Now they also tried a few other interesting things. They said, well, everyone uses ReLUs in these deep networks because they prevent the vanishing gradient, but maybe batch norm is so helpful that with batch norm we can actually replace the ReLUs with sigmoids, and it doesn't work great, but it still works. You can actually get up to almost the same accuracy as without batch norm and ReLUs. So just sort of an interesting thing they tried. So overall, when this original paper came out, it was this huge advance, and everyone started using it. And then a number of people started asking the question, well, why does this actually work? The explanations given by the original authors were maybe they didn't quite make sense. So there's a lot of further studies to try to explain exactly why this works. And one of the things that we can tell just from how it's designed, it's going to reduce variation across channels, because now all the channels will have predictable mean and variance, as well as all the layers. So that's one nice thing. And it turns out that it also helps to decouple layers. So because if you have a situation where some of the features in one layer are extremely big, and then you change them, that's going to have an effect on the next layer. By forcing them all to be around the same size, it helps to decouple the layers. When the layers are decoupled, they can be learned much faster. They don't have to depend on each other. And then further analyses show that actually, when you do this, the overall cost function of what you're solving gets smoother. So that's sort of interesting. So there's a lot of different explanations for why batch norm works. Helps to decouple layers, make cost function smoother, reduces variation. But the fact is, it works well, and it's very recommended procedure in most cases. Okay, any questions on batch norm? Okay. Okay, dropout is another technique that's very powerful. It's kind of a weird technique in that the idea is to temporarily remove a random subset of neurons in each mini batch. So this is a picture of maybe what standard neural network with, as you can see, like 4 or 3 layers would be. These are your inputs here, this is your output. And here you can see these arrows are essentially saying that each one of these hidden nodes can be affected by all the input nodes and so on. What dropout does is temporarily, it just removes some of those hidden nodes altogether from the network by multiplying them with 0. Okay, so, and it does this differently in every mini batch. So in one mini batch, it might have this pattern of turning them off. In the next mini batch, it has a different pattern of turning them off, and so on. So, and this is something you do during training, but you do not do this during testing. So it's kind of like during training, you're really giving your network a workout by just making its life really hard, by taking things out, and then during inference or test time, you allow it to work like this with all its neurons. So there's again, different explanations of why this helps, but one kind of convincing explanation is that when you do dropout, it's kind of like you're actually training an ensemble or a collection of simpler networks. This would be like one of the many simpler networks you're training, and that when you finally apply this network at test time, you're actually sort of averaging many of those simpler networks. And this ensembles is something we haven't studied yet. We're going to talk about it in the next unit. But when you ensemble techniques, it's a way of taking a lot of simple predictors and putting them together to make a really good predictor that's much more powerful than the simple ones. So again, we'll talk about that in the next unit, but that's a way of thinking about why dropout is working. Okay, so the basic way that this is implemented, and this is something that we do before dense layers, but you don't want to do this before convolutional layers because, it's just something specific to dense layers. So you take each of your activations. So this is activation for layer L, channel M, batch index I. You multiply it by a Bernoulli random variable, in other words, something that's 0 or non-zero. We'll call that D. And you're going to be multiplying it, or this random variable is going to have an on probability of P. And P is something that you need to choose. So usually P is 0.5, but sometimes you'll try 0.25 or 0.1 or 0.75, something like that. It's something you just got to try to see what works best. So let's imagine that your on probability is 1/3. So 1/3 of the time a given neuron is on, and 2/3 of the time it's off. So when you do that, you want to scale its value by 1/P whenever it's on. So if it's on 1/3 of the time, when it's on, you multiply it by 3. And the reason why is so that on average, it has the strength of 1 of being on. Okay, so the average value of these two numbers, when you choose the second one with probability P, is 1. So the reason why, if you didn't do this, then essentially it would be like at inference time, if you put in all the neurons, it would be like there's too many for how you trained it. So when you train it, when you do this with 1/P, it essentially means that let's say the average strength of any given neuron is always 1. Often it's 0, sometimes it's greater than 0, but its average strength is 1, and so it's a natural fit to when you use it at test time, when they all have a strength of 1. Is that making sense? Sort of? Okay. So, so this is something that's done during training. Full network is used during testing. And so a few comments are, dropout does make training more difficult. So one effect is that you often have to increase the number of training epochs when you use it. It also makes your network weaker. We say it reduces the capacity of the network because essentially, it's a lot of these nodes are just off when you're training it. So for that reason, you may need to make your network stronger. And what that usually means is you increase the width, or which equals the number of channels. You don't want to increase the depth. The depth is something you choose in advance, but it's easy to increase the width, the number of channels, when you use dropout. Okay, so finally, let's see, we're almost done with what I want to talk about today. Data augmentation is another trick that allows you to kind of artificially increase the size of your training data set. And it's sort of something that's specific to the type of data you're working with, but let's say you're working with images, like an image like this. Ways that you can make this single image look like different images, things like flipping it, shifting it, scaling it, rotating it, cropping it. So for example, this image was used to make this one. All we did here is we just zoomed in to a portion that's cropping, or we cropped in a different way to get this. So it almost looks like we have 3 different images, but really this is the same training image. So, and again, you could flip it horizontally for sure. Sometimes flipping things vertically is too big of a change because maybe we're training with a lot of images where there's sky on the top and not on the bottom, and if you flip them vertically, maybe you're actually creating a different training set. So flipping is typically horizontal, maybe or maybe not vertical. Another thing you can do is you can change the colors, like you can alter the colors in this image, color jitter, and maybe that's an allowable change. So it's just sort of a way of artificially increasing the size of the data set, and usually we see more data leads to better performance. Okay, so let's put all this. Let me cover this demo, and then we'll be done for today. So there's a demo that plays with these ideas, demo 9B. There's actually like 4 or 5 demos in this unit. So here you're using a convolutional neural network to classify CIFAR 10. So this is 32 by 32 color images, 10 classes. The CNN is simple. There's 2 convolutional layers with ReLU and max pooling, followed by 2 dense layers. And when we try this, we get 67% test accuracy after 100 epochs. So here I have the training accuracy versus epochs on the left, validation versus epochs on the right. And so you can see the number I'm talking about here, 67%, is where we are after 100 epochs validation. Now, as we know, training accuracy is not very useful. What happens with training accuracy, the blue curve, we're getting almost 100% for training accuracy. That's very typical for neural networks. It's actually the recommended way to train most neural networks is you want to see them maxing out on training accuracy, but that does not mean you're going to get 100% validation accuracy, right? Validation accuracy is what we really care about. Okay, so can we improve this validation accuracy? So the first thing we can do is we can add batch norm. And when we add batch norm, you get the orange curve. And you can see from the training perspective, it's pretty similar. But from the validation perspective, we got a pretty big boost of about 5% or so, right? Pretty good. What if we add dropout? So that's the green curve. So what's interesting about dropout, as I said, is the training accuracy now looks a lot worse. But remember that training accuracy we're talking about that's the performance of these networks where we've thrown out a lot of neurons. So we expect that these guys are not really going to do that well. When you put all the neurons back for validation, you get a huge boost. It's gone up here to almost 80%. Okay, so that's the power of dropout. The last thing we did in this demo is we used data augmentation, and for whatever reason, I'm not exactly sure why, it didn't really help. It's about the same, maybe a tiny bit worse. And I'm not sure, maybe the type of data augmentation we did wasn't great for CIFAR 10, or maybe we had enough data and it just didn't help us. I'm not exactly sure why, but for whatever reason, it didn't help that much. So that's just sort of an example of all these things, and you can see how it's all coded in PyTorch. There's another really nice demo here, and next time I'll cover this slide that we skipped here. All right, so that's enough for today. Sorry I went over time, and I'll see you guys on Friday.